Hello everyone, welcome to today's stream. So what I'm going to do today is I'm going to do some problems. I've got 5 problems on voltage, current, resistance, and capacitance. And these problems are problems in addition to the problem that I did during the what would have been a live stream last time if I hadn't had to postpone it. And I am going to do a problem similar to that problem actually, but for capacitors. But I'm going to go a little bit faster because once you get the idea of how these problems work, this is the multiple capacitor, multiple resistor problem. There's really no need to do them in detail over and over and over again. You could just rewatch one of them. So I don't know how long this stream will go, but it'll probably go for more than an hour. Okay. All right, so let's start. So the very first question is a simple question. It's what is the resistance of a 100-watt light bulb running at 120 volts? Okay, and that's like our incandescent light bulbs, and 120 volts is the voltage in the in the wall. And you go, well, how do I solve this problem? Okay, and you got to realize that this is a resistance problem, obviously, because I'm asking for the resistance. But resistors, what they do is they slow down current, okay, or they limit current, I should say. And by limiting current, the current wants to accelerate through there, or the charged particles want to accelerate through there. But it's because of like a friction at the electronic level that the kinetic energy of that current is being converted into heat. And so this is known as Joule heating, okay? And so the formula for that is basically this formula right here. Okay, it's P, which is the power, that's in watts, joules per second, okay, is equal to I times V, like that. And you look at this and you go, but wait a sec, I don't have either. I have V, but I don't have I, okay? And so how do I do this? Well, you could solve for I at this point, and that is one of the questions that I ask, what current is drawn, okay? And the way you would do that is using this, but you could also just go directly to the the resistance, and the way you do that is to couple this with the power definition of power, couple it with V is equal to IR, which is, let me write it down, V is equal to IR, which is Ohm's law, okay? And if you do that and you take a look at, I said page 6, let me just check if that's right, page 6 of the notes, you'll see that there's a couple of variations on this formula. And yes, I have them on page 6. Okay, you can either write this by using this and that together. You can eliminate either I or you can eliminate V. So you could write this as P is equal to one of them is I squared times I squared times R, or the other one is V squared divided by R. Okay, and so the reason I mention this is because, it depends what I give you in a problem. If I don't give you the current, in fact, that's one of the things I'm asking for, but I give you the power and I give you the voltage, you might say, oh, maybe I'll just use this one. And I ask for the resistance, okay? And what is the resistance? Okay, you might say, oh, maybe I'll just use this one. P is equal to V squared divided by R, like that. Okay, and of course we're solving for resistance, so let me multiply both sides by R first, okay, and then let me divide both sides by P, like that, and now we can go ahead and directly solve this. Okay, so the voltage was 120 volts, and we got to square that, and we don't need everything's in MKS, okay, and the power is 100 watts, like that. And remember, a watt is a joule per second, and so this turns out to be, let me use my calculator, divided by, turns out to be 144. And what are the units? Well, the units, because this is everything was in MKS, that's going to be in ohms. Okay, so there we go. There's our the first question. Okay, so the first question was for the resistance. Okay, let me just check my audio levels very quickly, because it looks like there's no one on the stream right now, so I usually expect you guys to yell at me if I'm muted. Yep, they're good. Okay, so all right, now we can say what current is drawn, and for this one, of course, you need. I guess you could go back, could even use this one at that point, okay? But you could go back and just use Ohm's law directly. V is equal to IR, and well, we want to rewrite that. We want I, and that's going to equal V divided by R, okay? And V is 120 volts, and R we found to be 144, and that turns out to be, I'll tell you in 1 second, 0.833 amps, okay? More likely, and that is the MKS value, but more likely I would convert that to milliamps, 833 milliamps, like that. Okay, so there's our first problem. Fairly simple, straightforward problem. But you know, if you don't know where to even start with something like this, you know, you might get a little bit confused, because you go, well, I know that there's a relationship between voltage, current, and resistance. Okay, and that's in fact how resistance is defined. That's Ohm's law. Okay, and you know that there is a relationship between power, current, and voltage. Okay, but I give you I ask for resistance, I give you power, and I ask for voltage. Okay, and so you say, well, how does that work out? And you could do this in 2 steps, or you could use these alternative forms here. Okay, so there you go. All right, next question. So done a lot of resistor problems right now. Let's do a capacitor problem. Okay, and this next one is basically just a definition of capacitor. Okay, and that one is actually on page 19. Let me check these pages, because I've got a feeling that I might have, that doesn't sound right. I'm not sure. Probably is. Oh yeah, it is. It is. Yeah. Yeah, on page 19 is where I start capacitance. Okay. I guess these notes were kind of long. All right. So if we apply 120 volts, again, it's kind of say from a socket in the wall. You got to watch it though. We didn't really talk about AC versus DC and direct current and alternating current. Our wall has alternating current, and so it wouldn't just charge up. You know, if you plugged in a capacitor, it wouldn't charge up, because the current alternates. First it goes one way, and then the other way. Okay, so but anyhow, let's suppose we had a DC supply of 120 volts, and we attach it to a 3 microfarad capacitor. How much charge is accumulated? And this goes directly to the definition of capacitance, and capacitance is equal to the charge accumulated divided by the voltage. Okay, like that. So you know, the capacitance in this case is 3 microfarad. Well, let me rearrange it. We're solving for charge, so we actually want to solve for Q there. So let me rewrite this as Q is equal to CV, like that. And the capacitance now is 3 microfarads. All right. And the voltage is 120 volts, like that. Okay. And now you got to be careful, because this is not exactly an MKS. It's that micro there. And you can do this in a couple of different ways. By this point, you've probably gotten good at these problems, and you know that all that micro means. Like, micro is just a short form for 10 to the exponent -6, like that. Okay, so you could put that in there, but chances are you're going to be pulling that out in a minute again, and like putting back another metric unit. So what you could do is you could just say, you know what, this is kind of a funny way to do it, write it, but you could say, look, I'm just going to kind of like factor out that micro. Like, so take this, like that. I'm just going to factor out that micro and put it back here. Okay, remember, it's literally just like multiplying by 10 to the -6. Okay, and you could just pull the factor out like that. Okay, and now you have a farad times a volt, and a farad times a volt is a coulomb. And so you're going to have 360. Q is equal to 360. That's the 3 times 120. Okay, and we have the farad times the volt, and that gives us a coulomb. Sorry. And there's that micro there, like that. Again, this kind of looks funny because we put the metric prefix in front, but I just kind of wanted to show you, maybe I could do it this way, F times V, like that. Okay, and the F times V, that gives you the coulomb, and then there's the micro, and so this is going to turn out to be 360 microcoulombs. Okay, so I hope that wasn't confusing. I just wanted to show you that you could literally just treat the little micro prefix here as if it were 10 to the -6. So every place you see, in fact, we can even think of it as having a multiplication in there, like that. So every place you see a micro, just think of like I'm multiplying by 10 to the -6. So of course, you know, you could just say, well, there's a 10 to the -6 there. Let's just put it at the end of the the factors to be multiplied. Okay, and then the answer is 360 microcoulombs. Okay, let me see if there's anyone in the chat right now. And it doesn't. That's okay. I mean, it just means that people will watch. I hope people will watch this later. But still gives you the opportunity to ask questions if you can. Okay, if you want to. All right. So here's number 3. Question number 3. What is a capacitor? It's a device which accumulates charge, and the way this happens is because you have two objects, and one of them becomes positively charged and the other one becomes negatively charged, and because they're in proximity to one another, the negative charges from one attract the positives from the other, and vice versa, and they kind of like being in that situation. Okay, and so you could charge up this capacitor, you can discharge it, and usually that's done with two parallel metal plates, okay, with some kind of a dielectric material in the middle, like glass or ceramic or something like that. But for people that are in biology or looking at or the health sciences, this is like cell membranes. All right, so this is we do in physics, we tend to think of these things in kind of the abstraction, but there really is this really is applicable to many different particular situations, and cell membranes is one example. Okay, in this one it's kind of an abstract problem. I say we want to build a 1 microfarad capacitor. By the way, that's pretty big. Okay, 1 microfarad capacitor. It's like 1,000. I'm sorry, milli. I apologize. 1 millifarad capacitor. That's like 1,000 microfarads. Okay, out of two parallel metal plates held 1 millimeter apart by ceramic material with a dielectric constant of 35. Okay, and the dielectric constant is kind of this enhancing constant. When you've got the two metal plates, each one kind of likes being near the other because one's positively charged, the other one's negatively charged, and so it helps to keep the charges in place. But if you've got a dielectric material in the middle, it helps mediate the electric field. In other words, it enhances the electric field inside of that, and it makes it even easier to put negative charges on one and and corresponding positive charges on the other. Okay, and so that's what that dielectric does. It's kind of like a multiplication factor. So without it, this capacitor would be 1/35 what it would be with that dielectric, or in other words, adding the dielectric increases the capacitance by a factor of 35. Okay, so if the plates are square, what's the length of each side? Okay, and I expect it to be big. I didn't solve the problem, but I expect this number to be pretty big because a millifarad is pretty big. Okay, so this equation is on on page 20. Let me just check that also. Yeah, it is. Okay, and the equation looks like C is equal to. So that's the capacitance of the that's the capacitance of the parallel plates. K is the dielectric constant, okay? And then you have epsilon naught, and let me get an epsilon from my word processor here like that. Okay, here we go. Paste that in there. Epsilon naught. That is known as the permittivity of free space. It's a funny kind of a name, but the way you should think about it is it's just the ability of space to sustain electric fields, okay? And if you put a material there, then it enhances the ability of space to sustain an electric field, and that's what that epsilon is. When we do magnetism after the test, you're going to see that there's an equivalent of that for magnetic fields known as the permeability of free space. So this one's the permittivity, the other one's the permeability. Everyone confuses them, so don't worry about that. I'm not going to ask you about the name. And it's just a number, which I'll give you. And then the other parts are, of course, the rest of it is the geometrical dimensions. There's the area of the two plates divided by the distance between them. Okay, so there's the formula we're going to use. All right, so what are we solving for? Well, we're solving for the length of one side, but to get the length of one side, that's basically the area, because the length of one side is just going to be the square root of the area. Like if the length of one side is x, then the area will be x squared. Okay, so let's solve for the area, and that's easy enough to do. I'm going to rearrange the equation first. I'm going to multiply so remember, we're solving for a here like that. So we're going to multiply. Let me do it in two steps. I'm going to multiply both sides by d, and then I get this. Okay, and then to isolate a, I'm going to divide both sides by the dielectric constant times epsilon. Okay, and that's going to give me CD on top divided by K epsilon on the bottom, like that. Okay, so there we go. And for this one, we better be careful working MKS units. Try not to be too fancy with the prefixes. So here, this is a millifarad. Milli is 10 to the minus 3. Okay, and so over here, this is going to be 10 to the exponent negative 3. All right, and we're going to multiply that by d. D is the distance between the two plates, and it's kind of hidden there. Let me just scroll down for a sec. So they're held a millimeter apart. A millimeter is a thousandth of a meter. That's 10 to the minus 3. Okay, so over here, times 10 to the minus 3. Okay, so there's the millifarad, there's the millimeter, and then divided by, and then we've got this factor for K here, which is 35. Okay, like that. Multiplied by, and epsilon naught is a number. Okay, and it's actually related to the Coulomb constant that we studied in the section on electricity, and the value is in MKS units is 8.854. Let me start writing this down. 8.854 times 10 to the minus 12, like that. Okay, and that's in MKS units. Now, what does that work out to be? It's good. Like I said, it's going to be a big number, but let me put that in my calculator. Turns out to be that number right there. MKS units, what are the MKS units for area? Meters squared. So meters squared, like that. And if you want the length of one side, remember, like I say, if x is the, I'll call it L. L is the length of one side, okay? Then the area would be L squared, like that. So if we got that L squared is equal to this number right there, okay, then L is going to equal the square root of this, okay? And what is the square root of that? It is way too big. It'd be like, you know, like each side of the square would be like 56.8 meters, okay? And that's pretty big, okay? So, you know, like 60 meters by 60 meters, okay? Or like 180 feet by 180 feet. So yeah, this is just not something that you would be able to build very easily. Okay, actually more like, I just did the calculator, more like 170, but still, you know, that's just very large. Capacitors in the lab, you know, they're just these like small cylinders, and what they are is they are parallel plates, but the parallel plates themselves are curled up, okay, so that you've got like a lot of area curled up within those capacitors. Okay, all right, so there's that question. Okay, and now we are going to get to this question right here. Now this is the larger question. This is like the capacitor equivalent of the question that I did on resistors. Okay, so find the effective capacitance of the given circuit. Well, I'll show it to you in a minute. With C1 is equal to 10 microfarads, C2 is 30, and C2 is 30, and C3 is 2.5 microfarads. And well, that's the first thing. Find the effective capacitance, and then the other is I want the voltage drop and the charge across each capacitor. Okay, for the multiple resistor problem, there, what you're going to look for is voltage drops and currents through each resistors. Here, it's going to be the the charge accumulated and the voltage drop across each. Okay, so let's take a look at what this looks like. Okay, so there you go, and now we can start to write in the numbers here. C1 I said was what did I say it was? Was 10. So this one's 10 microfarads. Okay. C2 was 30 microfarads. All right. And C3 was 2.5 microfarads. Okay, like that. All right. And you say, well, how do I solve this? Okay. So well, you have to find capacitors that are either in parallel or in series. Okay, and so you know, if like you might say, are these two in parallel? Well, the answer is no. It looks like they are because they kind of split there, but notice that that junction doesn't close in there. Okay, so you got to kind of find two capacitors that are purely in series or uh, in parallel, and you take a look at those two, and those two are in series. Okay, so we're going to take those two and we're going to place it with C1. We'll call it C12. Okay, so the index there, C12, refers to the fact that it's the reduced capacitor for both C1 and C2. Okay, so how do you do that? Well, you got to remember that with capacitors, if they're in series, how do they work? The reciprocals add. And capacitors in parallel, they just add. Okay? This is the exact opposite of what you expect with resistors, so keep that straight. Okay, and let me see roughly what page we're talking about for this. It looks like you know, if you're going to look at the notes later, page 22 I go over this. Okay, so actually on page 23 you've got the formulas. In parallel they add, and then the next page in series the reciprocals add. So let's go back to the picture here. 1 and 2 are in series. Okay, that means one after the other. So what does that mean? We have to add the reciprocals. Okay, so 1 divided by C12. So the reciprocal of the effective capacitance is 1 over C1 plus 1 over C2, like that. Okay, so there you go. That's the formula you're going to use. And you've got this. And what's that going to equal? 1 divided by C1 was 10. And we can actually work in microfarads, and then the answer will come out in microfarads, plus 1 divided by 30, like that. And that gives you C12 is equal to this number right there. Okay, that's not yet the answer because we want the reciprocal of that number, and the reciprocal of that number is 7.5. Okay, so C12 is 7.5, and since all the units that we were working with were microfarads, that answer comes out in microfarads. Okay, so there we go. We've answered the first question. The first question was, what's the effective capacitance? And just watch my language. Effective is usually used, but sometimes I say reduced. They both mean the same thing. It's like taking a bunch of capacitors and joining them together, series parallel, until you get down to one effective capacitor. Okay, so there's the effective capacitance for the whole circuit. No, we're not done. I apologize. The effective capacitance for just C12 is 7.5. We're not done because there's still one more capacitor. I apologize. Okay, so let's switch over to the whiteboard here, like that. And let me just quickly save this. Okay, now what? Well, this whole circuit, what's it going to look like? Well, see that the red circle there, we can replace it with one capacitor. And so I'll just redraw this. We have here basically this, like that. And we've got this, like that. Okay, it's still 20 volts across the whole circuit. This one was C3, which was, let me see if that's showing up. Yeah, it is. This one is C3, which was, what did I say it was? Geez. 2.5. Okay, so this one was 2.5 microcoulombs, and this one is now C1 and 2 joined together. Hold on, that doesn't look too good. Okay, C1, 2 like that, and that one is equal to 7.5 microcoulombs. Okay, so there we go. Let me save this one as well. Okay, great. So now what? Well, so I wasn't quite done. You know, now we have two, and you say, well, what do I do with these two? Well, they're obviously in parallel. Okay, and so those two are going to get joined together, like that. Those two will get joined together, and we can call that effective one C1, 2, 3, and that answers our question. Okay, so because they are in parallel, parallels add. So C1, 2, 3 is going to be C12 plus C3 like that. And C12 is 7.5. And C3 is 2.5. I give you that. Okay. And so obviously the effective capacitance for the whole circuit is 10 microfarads. All right, that answers the first question. Okay, let me take a quick look in the chat there. All right, so let me continue. All right, so we found the effective capacitance of the circuit. What is the voltage drop and charge across each capacitor? Okay, so let's go back to the this diagram right here. No, not that one. This one. Nope, not that one. Sorry, this one. There we go. Okay, so I'll do this in blue. All right, across the whole circuit, that is from here to there. Okay, if you were to put a voltmeter across there and like a multimeter and set it to measure voltage across those blue lines, and you're actually going to do that this week. Okay, so you know, you'll put here like that, and you'll be measuring voltage across there. Well, you know what the answer is. The answer has to be 20 volts because it's across all of these. Okay, now if you just say, well, you know what, rather than putting it across right from the terminals of the volts of the battery and measuring voltage, what if I just put it across there? Well, the voltage drop doesn't change along this segment, so this is still 20 there. Okay, and the voltage drop doesn't change along that segment, so that's still 0 there. And so hopping across C3, what's the voltage drop? It has to be 20. Okay, so let me clean that up. So the voltage drop across C3 is 20 volts, like that. Okay, and let's note that. All right, so back over here, I'm just going to write here voltage drop across C3 is 20 volts. Okay, and now what? Well, like for the resistor problems, what we would do is we would use Ohm's law over and over and over locally. Okay, and so we do V is equal to IR on each one of the resistors, and depending on which you knew and which you didn't know, you could find a third quantity. Okay, here we're not using Ohm's law, rather we're using this. We're using, where did I have it up here? This one. Okay, so it doesn't really have a name, it's just the definition of a capacitor, but this formula here is kind of used in the same way that you use Ohm's law in the resistor problem. So you take a look here and you go, well, do I have C3? Do I have the value of C3? Well, yeah, you do, because I told you it's 2.5, like that. And do I have the voltage? Yeah, well, I told you it's 20 volts. And so can I find the charge on C3? Yeah. So if I take this and I rearrange it, and I go Q is equal to CV like that, and just to not get confused because, there's a bunch of capacitors, let's say, well, this is on capacitor 3, this is a voltage drop across 3, and that's the charge on 3 like that. Okay, so C3 is 2.5 microfarads, okay, and the voltage is 20 volts like that, and so 20 times 2.5 is going to be, well, first I should just say, see the micro there? We can play the same trick that we did before. Let me actually do that on the next line, like this. Okay, it's a little different, but I think you're probably good at this at this point. So there's micro, let's just factor that out over here, like that. And now, what's a farad times a volt? A farad times a volt is a coulomb. So that part is going to give us the coulomb. So we can put that out here like that. Okay, so that was the farad times the volt, gave us the coulomb. Okay, and 20 times 2.5 is equal to 50, like that. And da-da, that tells us the charge accumulated on C3. Okay, so C3 has a charge of 50 microcoulombs. Okay, so all right, now what? Well, now we're going to look at the other two. Okay, so let's go over to here, and you say, well, how am I going to solve this one? So you know what? Let me clean this up me clean this diagram up a lot here. Okay, like that. So now we have a voltage drop across both of these, which we know has to be 20 volts like that. Okay, but it's not the voltage drop across one or the other. It's not the voltage drop across that one, and it's not the voltage drop across that one. It's the voltage drop across both of them. We know that the effective capacitance of both of them, C12, is 7.5 microfarads. Okay, and so we can find the charge accumulated on C12. Okay, and what does that mean, charge accumulated on C12? It's the charge accumulated on C1 and C2 combined together. Okay, it's like the effective charge that's on both of them. All right, so let's do that. All right, there's another way to do this too, but I think this is probably the easier way to do it. So instead of saying voltage drop across C3, we're going to say voltage drop across C12, which has a capacitance of 7.5 microcoulombs is microfarads is 20 volts. Okay, and you say, where did I get that? Well, that's where we calculated up here. Okay, so C12 is 7.5. Okay, like that. Now what? Well, now we use this formula again, like that. Okay, only now, and we want Q again, so we're going to use this formula here like that. We're going to rearrange it like that. But now it's not C3, it's C12, C12, Q12, and V12 like that. Okay, and C12 is 7.5. Okay, and V is that, like that. Okay, and that gives me that Q12 is equal to, all right, and just check out that the numbers are working. They are, good. That's going to give me 150. That's the 7.5 times the 20. The micro, okay, remember micro is 10 to the minus 6, but I'm just going to leave it as, rather than writing out 10 to the minus 6, I'm just going to leave it as micro. And F times V is a coulomb, like that. Okay, so there you go. Now, this did not exactly answer the question, what is the charge on C1 or C2? It is the charge on both of them together. But here's the thing about capacitors. So let me just take a quick aside here. Let me draw another picture for you like this. Okay, so in general, when you have a capacitor here like this, and then you have another capacitor here like this in series, so these two capacitors are in series. Suppose you place an electron here. So this is the negative side of the battery, and this is the positive side, like that. Okay. You see, is that showing up? It is, good. Okay, and suppose you push an electron onto there like that. Okay, and so you have one electron there. Well, that one electron is going to push an electron over to there like that. Okay, so you have an electron there. Of course, once there's an electron's moved over, it leaves a hole behind, and that's a positive. And now there's an electron here that really wants to get pulled off, and so then you get a positive there like that. Okay. Well, what if you get another electron? You know, because it isn't just going to be one. What if you get another electron move on there? Then that will be there. It'll push one off of there, leaving a hole behind and doing that, and like that. Okay, that means that the charge on, even if this is C1 and that's C2, the charge on this one is going to be Q, and the charge on this one is going to be Q. Okay, and so whenever two capacitors are in series, the charge on one is equal to the charge on the other. A little bit counterintuitive, because you say, wait a sec, they're two different capacitance. Yeah, I know, but the charge on C1 came from C2 and vice versa. So whatever the charge is on C1, that's the charge on C2. And guess what? That is the charge of C1, C2. Okay, and so if we go back to here, we can now say, and that would have been confusing, you know, for me to say, so Q1 is equal to Q2 is equal to 150 microcoulombs. You say, well, why is that? Why is it that? Because C1 and C2 are in series. Okay, that doesn't work in parallel, but it works in series. Okay, so we now know the remember what the problem says. The problem says, what is the voltage drop in charge across each capacitor? Okay, so how much charge is accumulated in each capacitor, and what is the voltage drop across each capacitor? So well, there it is. We've got it for C3. We know that C3 has a voltage drop of 20 and accumulates charge 50 microcoulombs. Okay. Over here, we know that the charge accumulated in C1 and C2 is 150 because the charge accumulated in the combined is 150, and they are in series. Okay. The only thing is what's the voltage across uh, uh, C1 and C2. Okay, we don't quite have that. We have the voltage. I shouldn't say that. I better be careful. We have the voltage across across the combined. That's 120. But what's the voltage drop across just C1, and what's the voltage drop just across C2? Okay, and we can use this formula right here to solve that. Okay, except that now we want voltages, and so we're going to rearrange that. So we multiply both sides by V, and then we divide both sides by Q, like that. All right. And we know Q is 150 microcoulombs. Oh, and I better put some, hold on, let me put some subscripts on this. So let's do it for number 1 first, like that. Okay. So Q1 is, well, that's the same for 1 and 2, but that's all right. Q1 is that, divided by C1. And C1 was, let's make sure we get it right, was 10 microfarads. Okay, so 10 microfarads like that. And notice how nicely the 2 micros will just cancel out. Okay, so they just cancel out. And so you get 150 divided by 10, that's easy, you get 15. The micros cancel out. And then you get a coulomb divided by a farad, and that's a volt. All right, like that. So the voltage across C1 is going to be 15 volts. 150 microcoulomb charge, 15 volts potential drop. Okay, so now what? Well, we'll do the same thing for C2. Okay, so instead of subscript 1, we'll have subscript 2 there, like that. And same numbers here, almost the same numbers, I should say. Okay, except that now it's going to, C2 is 30 microfarads, and 30 microfarads doing the same thing will give you 5 volts. Okay, so again, the 150 divided by 30 gives you 5. The micro divided by micro, that's like 10 to the minus 6 divided by 10 to the minus 6 gives you just 1. Coulomb divided by farad is a volt, and ta-da, there you go. So you have the voltage drops across them. Let's put this in the diagram, and I'll also make a little chart at the end to show you how that works. Okay, so oops, wrong. I guess no. There it is. Okay, so let me just clean this up a little bit. All right, so you can see there that across C1 and C2 you have 20 volts, the full voltage. Okay, and we just found that across C1, like that, we found 15 volts, and across C2 we found 5 volts. As a check, those had better add up. Remember, voltage drops are like walking downhill. The word drop has this sense of like a height associated with it. And so if you're at this point right here in the circuit, where I have that big red dot, you're at 20. You're at a height of 20 volts. You walk across the first resistor, the first capacitor to there, you've just walked down 15 volts. Okay. You walk across the next capacitor, and you've walked down another 5. So you've walked down a total of 15 plus 5 for a total of 20 across the whole circuit like that. Okay, and so yeah, it works out. Okay, and it's good to think in terms of these checks because these problems, they can get complicated, and there you go. Okay, so we're doing pretty good with time. Okay, so that solves that problem. Okay, and let me just summarize with a little chart here, and then we can move on. All right. So over here we could say capacitor, capacitor. Okay, here's the charge accumulated, and over here we can put voltage. Okay, just to make sure that we've solved them all. So the first one was C1. All right. Okay, and the charge across it was 150 microcoulombs. And the voltage drop across it was 15 volts, like that. Okay. And the next one was, let me just cut and paste this line, like that, was C2. C2 was 30. Same charge because they're in series. Remember, in series they have the same charge. And this one turned out to be 5, like that. And then C3 here. Okay, C3 was 2.5. Okay, and it had, I forgot now, oh, 50. Okay, it has a 50 microcoulomb, and the voltage drop across it was 20. Okay, and so there you go. That chart is basically summarizes the answer that I wanted for this problem. Is that because I asked for what's the charge on each capacitor and what is the voltage drop across each capacitor. Okay, let me take a quick look in the chat here, and all right, now it doesn't seem like anyone wanted to join the stream today. Not a problem. I mean, please do. Hope you watch this later, because you know this is going to be stuff that you'll need to be able to do the assignment, and also stuff that you'll need for the our last test. Okay. All right. Last question, okay, and this is one of those RC circuit questions, okay? So we have to watch this because with RC circuits, you have a couple of things going on. One, they're exponential, okay? And also the formula that's involved is either the charging up formula or the discharging formula. They're a little different, and if you get the wrong one, you'll get, of course, the wrong answer, okay? So let's read through this problem. I'll draw the circuit for you, although it's not that, interesting to draw it. I'll still draw it for you, and then we'll solve the problem. Okay, so we build an RC circuit using a 37 kilo ohm resistor and a 67.5 microfarad capacitor. Okay, what is the time constant? And the time constant is this characteristic constant, which is in seconds, that says something about how quickly the capacitor either charges up or discharges. Okay, so all right, let's continue. If the circuit is hooked up to a 20-volt battery, oh, that's not how you spell battery. That's all right. I'll fix it in a second. How long does it take to charge up to 75% of a maximum charge? Okay, and what is the maximum charge? Okay, this stuff is on page 31 of the notes. Okay, and let me just take a look at what I have on page 31 so I can guide you to the correct formula. Yes, on page 31 we have the formula for charging up, and on the following page we have the discharging. Okay, so let's be careful. First, let's solve the time constant. Well, let me just draw the circuit so you know what it looks like. Okay, because if you saw this circuit and I didn't call it an RC circuit, you might go, well, how do I solve the what circuit should I be looking at? And the way an RC circuit works is that it has a resistor. Oh, terrible. Okay, we have a resistor like this in series with a capacitor like this. Okay, and we're going to charge it up, but we got a little switch there like that. This is how you draw a switch. Okay, and then there's a battery like this, and it doesn't matter which way is positive or negative. Okay, and what happens is that right now there's no charge on the capacitor and there's no current flowing through the resistor. But as soon as you close that switch, okay, charge will start to flow this way onto the capacitor, and it'll flow through this like that with the switch closed, and you'll get a current. But it's a transient current, because what happens is that as the current starts to flow, it starts to charge up the capacitor, and the capacitor can't charge up to infinity, okay, because the battery just doesn't have the voltage to push all that current, all that charge onto it. Okay, and so what limits how much, how quickly this charges up is not only the capacitor, because the bigger the capacitor, the longer it'll take, but also the resistor, because the bigger the resistor, also the longer it'll take, because the resistor is going to limit the current. Okay, and the capacitor is going to limit how much charge you can get on it. All right, so there's a little bit of a refresher of the underlying physics. Here's the formula that you want. For the time constant, it's tau, and let me grab that symbol. It looks like the T. Well, you've seen tau because with torque, you saw it before. But it looks like a T, but it's actually this symbol right here. Okay, like that. Okay, and tau is equal to RC. Okay, it's just R times C. The bigger R is, the longer it takes to charge up. The bigger C is, the longer it takes to charge up. Okay, so both of those things will increase how long it takes to charge up. All right, so easy enough. R is going to be 37 kilo ohms like that. Okay, and C is 67.5 microfarads like that. Okay, and you go, geez, how does this work out? Kilo is 10 to the 3, micro is 10 to the minus 6, and so you're going to say, well, how does that work out? Okay, well, what's going to happen here? Well, we better, you know what? We better just put this one in MKS. Okay, so like that, and we'll just rewrite that. The K there, that's going to be times 10 to the exponent 3. Kilo is 10 to the 3. Micro is times 10 to the negative 6, like that. Okay, and now the units look funny because you've got an ohm out here. Let me just pull the units out. And you got a farad out here like that. Let me pull that out. Okay, whoops. All right, like that. And you go, geez, what's an ohm times a farad? And I actually showed this in the pre-recorded lecture. This is a funny unit, or a funny combination of units. It actually just reduces to seconds, and that's what you expect. That's why it's called a time constant, because it measures time, and time is measured in seconds. So an ohm times a farad is basically a second, like that. If you want to know what's going on there, the time is coming from the resistor. Okay, the time is coming from the resistor. Okay, so all the other units, all the coulombs and the volts and all that, they cancel out, but there's this extra time in the ohms, and that's the only part that survives, and therefore this is a time constant. Okay, so now what? Well, just multiply this together on your calculator, and you get a number. Let me see what that number is. It's this. Okay, so tau is equal to this number there, like that. Okay, so I'm going to round it off to 2.5 seconds. Okay, now 37 kilo resistor, easy. No, you'll see those in the lab this week. Okay, 67.5 microfarads. That's a bit big. Okay, that's a little bit big. A little. I mean, you can have them in the lab, but I mean, this is about as big as you're going to get. Okay, for a lab size capacitor. All right. And there you go. You get a time constant of 2.5. Now, what is that time constant? So let me just draw the next thing for you. I'll do this on the same diagram as before. So what happens is that if you were to plot the charge on the capacitor versus time, like that. Okay, see if, yeah, good, that's showing up. Okay, what happens is it actually starts at t equals 0. That's when you close the switch. Of course, the charge is 0, but then it builds up, and it reaches a maximum, like that, a Q max. Okay, and whether it does it like that or whether it takes a long time to, okay, or it does it very quickly, like that, that depends on what your tau is. Okay, so that's why tau is kind of a measure of how quickly it builds up. Okay, now the next thing is, let's read this question again carefully. If the circuit is hooked up to a 20-volt battery, okay, how long does it take to charge up to 75% of maximum charge? Okay, so for this you need the formula, and it's the charging up formula. That's the one that is on, take a look here. It's on page 30, okay? Sorry, 31, okay? And it looks like this. Q, that's the charge at any given time, is going to equal Q, and what did I call it? Q naught, I think? Yeah, Q naught. Q naught is Q max, okay? 1 minus the exponential of negative t divided by tau, okay? So you say, geez, what's this formula all about? So let me just tell you that Q naught is max charge. Okay, in fact, that's one of the questions that I'm asking for, right? I'm asking for what is the maximum charge. That's the second part of this. Okay, so Q is how much charge is on it at any given time. So this part, that little t that I put there like that in brackets, that just means functional dependence. Okay, so Q has a functional dependence on time. Q changes over time. Okay, so Q at a given time is given by this formula. Okay, like that. All right, and let's see if we can plug in the numbers. You say, well, wait a second, you don't know Q naught, and we're going to try to find T. So how do you do this? So 75% of maximum charge. Well, what does 75% of maximum charge means? It means that if you take this formula and you rewrite it like this, divide both sides by Q naught, like that, okay? That ratio, Q to Q naught, it can't go over 100%. That's totally charged. It starts at 0% uncharged, and it builds up 10% charge, 20% max, 30% max, 40% max, and so on. And when it gets to 100%, that's it. It just stops, okay? And what did I say? We want to know how long it takes to reach 75%. So this Q over Q naught must equal 75%. Okay, so we could just put 75% in there. All right, like that. 75% is equal to the rest of this. Okay, now we know what tau is, but I'm not going to write it in right now because it's annoying to, I'm going to have to manipulate this. So there it is. And 75%, you want to write that as 0.75, like that. Okay, there you go. Now what? Well, now we can actually get rid of those outer brackets like that. You're trying to solve for t. Remember, you know tau, but you're trying to solve for t, and you go, well, geez, how do I unpack this? Because t is buried inside this scary exponential here. So the first thing is, let's isolate the exponential. Okay, so we could do that by just subtracting 1 from both sides. Okay, and if I subtract 1 from that side, I get that. Okay, and 0.75 minus 1 is going to be negative 0.25, and that's going to equal negative the exponential like that. Okay, and of course there's a negative on both sides, so let's just get rid of that. And now there we go, we get to this point here, we have the exponential isolated. In fact, let me write it, oh, why did I do that? Let me just write it the other way around like that. Okay, so I just turn the 2 around. Okay, now what? Well, now you say, well, how do I unpack an exponential? And this is the magic of inverse functions. Remember, there's the tangent, and then there's the inverse tangent. If you take an angle and you tangent it, you get a number. And you say, well, now that I have this number, I want to go back to the tangent. Well, then you inverse tangent. Okay, so you have an exponential, and you want to inverse the exponential. So suppose you have this equation here. Let me just do it to the side here. Okay, this equation here has the form exponential of a is equal to b. Okay, now you can always do the natural log of both sides. Okay, you can always, whatever you do to one side, you do to the other side. Okay, you just have to be careful when you do things like divide by 0 and stuff like that. But generally speaking, whatever you do to one side of the equation, you can do to the other side of the equation and preserve the equality. So over here, I'm going to take the natural log of this side, and I'm going to take the natural log of that side, like that. And now it looks worse, except that log and exponentiation have the relationship of function and anti-function or inverse function. Okay, and so the log and the exponentiation, they undo one another. It's like if you start with a, you exponentiate it, and then you log it, you're back to a. Okay, so all of this is just a, like that. All right, so take a look. A was like that. All right, so there's like a is equal to, and b was like the 2.5 is going to equal to the natural log of 0.25, like that. All right. Great. Now what? Well, let's actually do the natural log of 2.5. You got to do that on your calculator. So where's my natural log? There it is, 0.25, and it's actually equal to this number right here. Okay. So we get that this is equal to that. All right. All right. By the way, the log of a number bigger than 1 is positive. The log of a number less than 1 is negative. Okay, so that's why you see the negative. So there's a negative on both sides, so we could just get rid of that negative there like that. Okay, and now what? Well, don't forget, we know what tau is equal to, so we can simply multiply that on both sides, or I could just write it in there like, there's tau, and you say, but what is tau? Well, we found tau to be 2.5. Well, I'll just use all those decimals there like that. So I could just take that out and put that in there like that. Okay, and now what? Well, multiply both sides. Okay, so multiply that 2.4975 by that very long number there, and you will get that t is equal to, what is it equal to? Let me do that on the calculator. It's equal to, and I won't give you all the decimals, but there it is. 3.46 seconds. 3.46 seconds. Okay. So what this says is that as soon as you close that switch, the capacitor starts to charge up. Okay, and as it's charging up, it's going to pass, and it's going to get to 100 eventually, but it's going to pass the 75% mark. Okay, 75% charge. And you see, at what time does that happen? At 3.46 seconds. Okay, and now you could sort of see what that characteristic time tells you. That characteristic time is saying, like things on this circuit. They say something like this: things on this circuit happen within. Whoa, what did I just do? Sorry, I just minimized the wrong window. Things on this circuit happen on order of 2.5 seconds. Okay, and so to reach 75%, is that an order of 2.5 seconds? Yeah, it's a little bit more, but it's the same. Okay. Now, you have some circuits which are like in the milliseconds, and then you'd expect all things to happen within millisecond time scales, and some of them might even be down in the microseconds, in which case you expect all your answers to be roughly in the microsecond range. Okay. And here we're at 2.5 seconds. You expect everything to be happening in roughly the 2.5 second range. Okay. And we're almost done. What is the maximum charge? So for the maximum charge, let me go back to the whiteboard here. The maximum charge, you see what's happening is again, the switch is closed. You just keep pushing current on there. But of course, it just keeps building up, building up, building up. Once it builds up, the current eventually stops. Okay, and then the resistor is like it isn't even in the circuit. So the circuit, once it's charged up, effectively is just a capacitor. And the resistor is doing nothing because there's no current, and there's a battery there like this. Okay. And so you've got a capacitor here like that, and you've got a battery here like that. And again, there's no current, so the fact that there's a resistor there doesn't make any difference whatsoever. And so for a capacitor in a circuit with a potential V, the charge that you're going to get is given by C is equal to Q divided by V, like that. Now we're looking for Q, so it's going to equal this, C times V, like that. Okay, and now we can put that little knot in there like that, because that is the max. That's your max. Okay. Once the current stops, it's kind of counterintuitive, but once the current stops, you've reached maximum charge. Okay, but that happens when there is no current. The resistor has nothing to resist. Okay, it's purely potential that's holding the charge on that capacitor. Okay, and so basically it just reduces down to C is equal to Q over V. Okay, and so now C we said was, well, let's go get the number, 67.5 microfarads, like that. All right, and the voltage was, we didn't need the battery up till now, but now we do, 20 volts, like that. And what are we going to do? We're going to have this is equal to, well, the micro, again, the micro we could just, here, let me just write the whole thing out. Like that. Copy, paste. Okay. So the micro, let's just pull that out. Okay, remember, that's just like a 10 to the minus 6. Okay, so there, that factor is just there. A farad times a volt, well, we've seen this already, and that's a coulomb, like that. And so it's just going to be this number here. Let me get that on the calculator. All right, it's going to equal that. All right, and now maybe it's good to show you what that 10 to the minus 6 I'll do this in two ways. Like on a test, I probably wouldn't give that as an answer. I would probably give this as an answer, a 1.35 millicoulombs, like that. Okay, now what happened? How did the micro go to milli? Well, if I move the decimal over 1, 2, 3 to the left, basically, it's like I'm shifting the 10 to the minus 3 out of that to this number here, and then there's still 10 to the minus 3 left over there, and that gives me the milli. Okay, so that's one way to think about it, or probably the better way to do it, or the safest way to do it, is to just take that out, that micro there, multiply by 10 to the caret negative 6, like that. Okay, and now if you do this on your calculator, you're gonna and your calculator properly moves the decimal over, it'll be 3.5 times 10 to the negative 3 coulombs. Okay, so again, we're at -6 here, -5, -4, -3. All right, like that. And so this is going to be times 10 to the negative 3. But 10 to the negative 3 is another name for milli. So it's 1.35 millicoulombs. Okay, and that's how you would generally, that's what I do on a test. I always use the most economic metric prefix, okay, because that's what's done in the real world, okay. And so the answer is 1.35 microcoulombs. All right, it wouldn't reach that right away. It's going to take some time, but eventually it'll get up to 1.3 microcoulombs charge on the capacitor and no more. Okay, so went a little faster than I expected. That's because I went a little faster on the capacitor problem than I did for the resistor problem. But let me just take a quick look in the chat here, and there was a couple of people that popped in, but all right. So I don't see any questions, and that's all right. That's the reason to do these live streams, so that you can either participate in them and ask questions, and you say, well, I don't really feel I need to ask questions, but I'll watch it later. You can watch it later, okay? And there we go. So I'll say something more next week about the test. Hopefully you guys have watched this to the end of the video, but basically the test is not going to include this material on voltage, currents, resistors, and capacitor, because that's would make test 2 too big and test 3 too small. So it's just going to be the sound, thermodynamics, and the introduction to electricity. All right, and this material that I did now and that I did last week, that'll be transferred to test 3. What happened this year is Easter fell right on the date, right in the week where I normally do the test, and I guess I could have done the test earlier in that week and that would have worked out, but I decided to move it to a week later, and we had to move the labs to a week later anyhow. So that's the reason for doing that. But then that unbalances test 2 and test 3. So that's why it worked out this way. Okay, so all right, well, there you go. And of course, if you have any questions, shoot me an email or jump in on one of the Jetsy live chats. Okay.